Hey everyone, welcome to my penultimate lecture in this computer vision course. It's pretty crazy. We've already made it to almost the end. I hope you've enjoyed the class so far. We are really getting close. It's pretty crazy. So let me go ahead and ask Arvind and Rohan if they have any announcements today. Arvind, are we ready to make an announcement about the final format and everything for the presentations?
Yeah, I just wanted to share my screen and
That'd be great. Yep. Thank you so much.
go through the instructions.
Perfect.
My screen is visible, right?
Yep, got it.
Okay. Hello everyone. So for the final presentation, we have planned synchronous mode instead of the asynchronous mode which we have planned earlier. So we have divided all the groups into two parts: the one with industrial partners and one without industrial partners. The one with industrial partners, they have to schedule a meeting with their corresponding industrial partner, work with them, just email them sooner so that you'll have time to present them before 23rd. And also please share the meeting link, the date and time with the professor and the TAs so that if possible we can also join the meeting. And the groups with the industrial partners are supposed to record the entire presentation session and submit it on Canvas so that we can evaluate it. And you have to submit it before 23rd of December, which is the last date of fall 2020. In the worst case scenario, if your industrial partner cannot make it for the meeting, you'll present it to the professor and the TS and we'll contact you directly. And coming to the groups without industrial partners, according to the schedule of the exam schedule on UNCC website, we have 2 p.m. to 4:30 between on 22nd December. So all the 5 groups would be presenting it slot by slot. Slots are given here. And the meeting link would be the regular Zoom link, which you guys join every time. And the deliverables would be a demo of your project, a public GitHub repo link, which contains all your work, and the presentation slides. One of the group members can submit, that should be sufficient. And the final deadline is 16th. That's it.
Great, thank you, Arvind. Perfect, thank you. If you guys have any questions about that, please throw it in the chat window now or just shoot us an email. So I hope this format works well. You know, it's funny, if we think back to the beginning of the semester, remember Arvind and Rohan, we thought there was a chance we'd have final presentations in person, which sounds laughable now, right?
Yeah.
So we've had to kind of adjust the plan along the way. So I think this will work well for everyone. We're really looking forward to hearing everyone's final presentations. And if you have any questions, we haven't provided, very strict guidelines about the PowerPoint decks or anything. If you have any questions, just email us. If we see a bunch of the same question, we'll make an announcement about it. But, just generally, we have a guideline in there. I think we said 15 or less slides. Is that right, guys?
Yes, Professor.
Okay, great, yeah. And in those slides, we're looking to hear a bit of a story. What problem are you trying to solve? What makes it hard? What challenges did you run into? Ultimately, some of the groups out there, we've talked to quite a few of you, all of you really. So some groups are have figured things out and their models are working great. Some groups are still figuring it out, and that's okay. And some groups, you're not going to get everything to work that you wanted to, and that's okay. You're supposed to take a little bit of a risk in this project. I don't want you doing boring stuff, right? I want you to do stuff that can really make an impact and might fail, and that's okay. If it turns out that your model doesn't do as well as you thought or this struggles, the really important thing is to just be open about that in your presentation and share what you tried and share what the struggles were and present hypotheses as to what some of the problems were and what you could do differently going forward. So I'm not saying that we won't grade you on your performance. We are looking for good models, of course, but we do know that there is risk in doing these projects. And the main point I'm trying to make is that if things are really not converging or not training as you'd like them to, get done what you can, but still present the whole story. Don't take away parts of the narrative or the story of what you did just because they don't work. That part's interesting too. So we're looking for the full story of what your group worked on. And yeah, we're really looking forward to it. Any other announcements or anything to add to that, Arvind and Rohan?
Yeah, also make sure to put your presentation somewhere between 15 to 20 minutes so that we could
Yep.
get some time to ask our questions as well.
Yeah, because I think for the groups without industry partners, we have it looks like 25 minutes blocked off per group.
Yes, Professor.
Okay, great. Yeah. So, and if it ends up being a little shorter, I'd say as short as 10 minutes is fine for your presentation. That leaves us 10 or 15 for Q&A. But don't go over 15 or 20, right? 20 is probably too long, right, for your presentation. 15 would be great, and then I think 10 is probably fine too. And I think roughly the same rules would apply for your industry partner. If you only have 30 minutes for your industry partner, I would plan on 10 to 15 minutes of presentation and then Q&A, and just be ready to discuss other angles they may want to talk about. With these presentations in general, the more interactive you can make it and the more dialogue you can have, the better.
Yeah, also the groups with industrial partners, please let your industrial partner know that you're recording the session for
Oh yeah,
evaluation purposes.
thank you. Yeah, thanks for mentioning that. And that will be private, so we won't put that on YouTube or anything. It's just for private evaluation purposes.
And also just make sure to record the session, because if you start the session and you forgot to record it, it's again difficult to present it to the industrial partner. So make sure
Yes.
you record it
Yep.
and
Great.
let them know that you're recording the session only for evaluation purposes.
Perfect.
That's it,
Okay.
Professor.
Great, wonderful. Anything else, Arvind and Rohan? We didn't have a chance to discuss outside of class. It's been a little bit of a busy week. Did we decide to use the same groups as the projects for the programming challenge?
Yes, Professor. I've already
Okay,
made an announcement.
wonderful. Thank you so much, Arvind. You are ahead of the game, ahead of the curve as usual. Great. Okay, cool. Any other announcements or things, Arvind or Rohan?
Nothing. That's it, Professor.
All right. Okay, great. All right, well, let's hop into it. We've got a couple lectures left here, and we're doing 3D computer vision. I hope it's been interesting so far. So let me go ahead and do a screen share here. Let's see. Okay,
Just wanted to add one more thing.
yeah, go ahead.
This is the last week for your project meetings. So there are, I guess, 6 groups who have meetings scheduled for this week. It's 4, 5, 6, and 10, 11, 12. Yeah. So just check the schedule and book your slots for the meetings.
Yep, thank you, Arvin. Yep, so last week for project meetings. Yep, that's right. Here we are. Yep. So yeah, make sure your project meeting's booked. And then, yep. Great. All right. Okay, so we have made it all the way. Well, let's pick up where we left off last time. So last time we were going a little faster than I wanted, which I never like to do. I should just go slower. It's okay to not cover everything. It's better to cover less well than it is to cover more poorly. So let's go back a little bit to interest point detection. And I want to make sure we cover the big concepts here. Because if you do any kind of work in computer vision and some of your projects are using interest points, that they come up a lot. So I'd like to make sure that you have at least a passing under. And just to summarize the idea of interest points again briefly, the idea, and this is, I would say this is a little bit older computer vision than the stuff we've been doing with deep learning, but it's still very valuable and used all over the world in all kinds of applications. A number of these tasks are really not well suited for deep learning. We will see a deep learning approach to this problem at the end of this lecture, but it's still not, there's a number of things where you really don't want to apply deep learning. And even if you do apply deep learning, understanding the underlying principles is still a good use of time. So the idea we were talking about is tracking key points, right? Tracking key points either from frame to frame in a video or to match up 2 different images of the same thing. And I didn't talk about this a lot last time, but just as far as the application, so like why do you want to find key points? There's a bunch of reasons you may want to look at key points. So we mentioned earlier the idea of 3D reconstruction, right? So if you go to the GitHub page for this module, and this module is called the 3D world, then you'll see a cool demo from a company called Mapillary where they make 3D maps from images. If you go to Mapillary's website, they do have a map of Charlotte. I believe you can go look at it. It's pretty cool. But this is one of the things you can do with key points. You can make these 3D maps. And the key points are just one part of your pipeline, but they are an important part, a really important part. You could do a bunch of other stuff with key points like object tracking, stereo camera depth estimation. Just real quick, we haven't talked about this formally in this class. What do I mean by stereo camera? What does that mean? Does anyone know? Yeah, multiple cameras. And stereo means not multiple. It doesn't mean multiple, but it means exactly two, basically. So stereo means two cameras. And what applications would it make sense to use two cameras? Why would we ever want to use two cameras? What could that help us do? Any ideas? Why have two cameras? What kinds of problems could that help us solve? Avoid things, sure. So Hernan says avoid things. Okay. Um, I guess we haven't talked about this a lot in this class, right? So cameras are kind of like eyeballs, right? And yeah, so Diego has it. So I was kind of trying to lead you towards the idea of depth perception. And the idea is using two cameras, you can do some math to figure out how far away things are, and basically triangulate the distance to objects. It works okay for cameras. There's a bunch of math out there you can use. We don't cover 3D depth perception using stereo cameras in this class. There's a bunch of literature on it. You can check it out. But it's not, I would say, the most popular robotics technique today. In fact, some of the deep learning based depth estimation does better in some cases, and it can be a little bit finicky. Stereo depth estimation is very sensitive to camera calibration, and if your cameras aren't well calibrated, it can be very difficult to get good performance. So it's a really cool idea, and maybe it'll come back, but today it's not terribly popular in some areas of robotics for sure. And also, if you look at, I think it's Subarus. If next time you see a new Subaru, look at the camera orientation. Subarus they use two cameras, and they're kind of spaced apart for their driver safety systems, and they're doing some kind of stereo computation, I'm sure. So it is out there. It's a cool technology. Let's see here. What else can we do with key points? We can do, oh yes, SLAM. So SLAM is a really cool problem. Google around for this if you're interested. This is where you have a robot kind of drive around an area and simultaneously figure out where it is and build a map of the area. So yeah, Diego says, do robots use LiDAR instead? That's a great question. So it depends on how serious your robot is, right? So let's take the most popular robot in the world, probably the Tesla Model S. You could argue that's kind of a robot because it can drive semi-autonomously. And there's a more popular robot, but it's one of the more popular ones. So does anyone know how does Tesla do depth perception? Does anyone know how they figure out how far away stuff is? So yeah, Akshay says using cameras only. That's almost true, almost. They do use cameras, that's part of it. They use one more sensor though. Does anyone know the other sensor that Tesla uses besides cameras? It's very popular in aviation. Yeah, close. So sonar is a good guess. They do use sonar, but sonar has a really crappy range. So sonar can go for like 5 or 10 feet and then it dies off. So they use sonar for like the surround, like if there's a vehicle in your blind spot, they use sonar to find that. But there's another sensor they use. It's actually radar. So they use radar to help estimate the distance to objects. So radar is a very, very effective technology in aviation. You send out electromagnetic pulses, they bounce off an airplane, it comes back. It's not as easy to use in autonomous driving, but it is. It's better than vision in many contexts to find depth. But they don't use stereo. Okay, and then like Waymo uses lidar, just like Diego was asking about. So there's other things you can do with key points. Another example, so you maybe on your phone, you've taken a panoramic image before. If you've done that, the algorithm in your phone probably used key points to stitch the multiple images together. So that's a cool application of key points. And there's a bunch more stuff you can do with them, but they're a big part of a lot of computer vision pipelines. So that's why we're spending a little bit of time studying them in this class. And we went through the history a little bit last time. We talked about Moravec's corner detector very briefly. We talked about the Harrison-Stevens edge detector or corner detector. Excuse me. We ran some algorithms. We found some corners. We did some filtering. Let's see. That wasn't super exciting. Then we used this good features to track method. That gave us some kind of better features here. And then to track them, we used a method called sparse optical flow, or Lucas-Canade optical flow in this case, a very specific implementation of optical flow. And using that approach, we searched around the neighborhood of every pixel, or not of every key point, excuse me, and to see where that key point had moved to in the next image. And doing that, we were able to create these optical flow kind of animations where we, find a key point in 2 frames and we compare them and we try to match them, and we use that to estimate the motion between sequential frames. So that's the idea here. And we saw that it broke down, right? So when our step size was 10, we didn't do nearly as well, right? We had all this noise. And it's because the image has changed too much. Here we're taking images that are 10 steps apart, and they change too much. It's hard to track, right? So that's the idea. So to address this, we learned about a different approach called, really this is kind of key point matching, really is the name of this approach. But one of the main algorithms as part of this approach is an algorithm called SIFT. We started just discussing how SIFT worked a little bit. I really didn't give you a lot of detail. And that's kind of intentional. If you would like to read more about it, please do. But for now, I would say just know that there's a method called SIFT that does a very good job at finding key points that are good at tracking, that are good to track between images. And it also, not only does it find key points, it gives you what's called a key point descriptor that allows you to match key points between frames. So that's the idea. SIFT is patented, or it was patented, so it's kind of hard to find good implementations of it. So another alternative you can use is ORB. One of our groups, I'm not sure if they're on right now, but one of our groups has tried SIFT and ORB, and their ORB model did not do so great, so they've shifted to SIFT. That's been my experience too. ORB is good, but SIFT is a little bit better. But ORB is another algorithm that allows you to detect and match key points. And we're about to do some ORB, basically. So let's kind of walk through some ORB. So again, we're using the OpenCV library. So we create this ORB object. So let's see, a question came in. Oh yeah, so Hernan says you found SIFT is not real time, it's very slow. Interesting. Yeah, so if you look at the title, Hernan, see I forgot that's Hernan's group. That's awesome, cool. So yeah, look at the title of the ORB paper, right? So the title is ORB, an efficient alternative to SIFT and SURF. So by efficient, they mean, hey, it's gonna be faster, right? So it is a lot faster, right? So yeah, absolutely. So if you're doing a real-time application, then something to take into account. I think there are optimized versions of SIFT that can run reasonably fast, but yeah, look at my note right here, right? So it's 2 orders of magnitude faster to run ORB. That's pretty cool. So here's our ORB key points. We kind of have a similar problem to what we saw before. What problem do you kind of see when you look at this image? What's kind of weird about the key points we've detected? What do you notice? Yeah, they're only on the brick. Thank you, Austin. Yeah, totally. Does anyone know why? I barely told you how ORB works, right? But any theories, right? Why more the brick? Yeah, it's the texture. So feature detectors like ORB look for regions that have a lot of texture going on. That's like a high signal. And the brick is very textury, right? There are ways to spread these out to make it be more on the cylinder, for example. We won't cover that in this lecture, but there are things you can do. For now, we're going to kind of live with it. We'll see what we can do despite that. So those are our ORB features. Now I want to spend a little bit of time talking about descriptors. So the idea of a descriptor is it's like a vector that represents a little image patch or a key point, and it's supposed to be robust to things like changes in position or changes in lighting. So let me get into that in a little more detail just to show you what I really mean. So what I've done here is, let me show you where DES came from actually first. So here we go. So when I run the ORB detector, right here I'm running the ORB detector, and I get out a list of key points, which is not surprising. Here's the key points plotted, but I also get out a list of descriptors. And what those descriptors are, like I said, for every point you get a vector, and the vector is supposed to be a robust description of what that key point kind of looks like. That's the idea. So we get out these descriptors. Here's the shape of my descriptors, 1466 by 32. And this is my favorite question to ask you in this class. You probably noticed, and it's on purpose. So, and of course, I've misspelled the question. Dimension. Okay. Yeah, so the dimension, notice the dimension of our descriptors is 1466 by 32. Why? Any ideas? Why is that the dimension of the orb descriptors that our algorithm has computed for this image? What does the 1466 mean? What does the 32 mean? Any ideas? Yeah, so thank you, Abhijit. So it's 1466 points. Yeah, and notice that I set up Orb to search for 2,000 features. It didn't find 2,000 features that it really liked. It found 1466. So yeah, so the 1466, that's the number of features or of key points that we found, right? Thank you very much. And then yeah, so what must the 32 be? What does that represent here? So yeah, so good guess. So Austin is asking if it's the number of images. So no, it's a great guess. We've only fed it one image. So I'm going over the code a little bit fast here, but I've created this orb object that's supposed to search for 2,000 features. I've passed in this one image called gray one. I haven't passed in any more options. You can pass options here if you want, but I haven't. And I get back key points and descriptors. Yeah, so it's only one image. So any other theories? We've got 1,466 rows and 32 columns. So gradient is a good guess. Let me actually, I'm kind of pointing out what a descriptor is. Yeah, so sure. So Abhijit says it's a 3D point in 32D. Sure, you can think about it that way. A descriptor for a key point, it's just a vector. It's a vector that is supposed to be unique to that key point. That's the idea. We won't cover how it's computed exactly here. I alluded to it last lecture when I talked about this. So when we make a key point descriptor, this is how SIFT does it. There's other ways to do it though. But what SIFT does is it computes what's called a histogram of gradients, basically. So like for this region, you compute, okay, how many arrows are pointing up, and you added them all together, right? You add all the up components, and you add all the right components, right? So you get kind of a direction that the average of this little grid is pointing in. And then you take all those directions. Notice there are, how many arrows are there here? There's 8 arrows here, 8 here, 8 here, and 8 here. So that's 32 numbers, and you just put them in a vector. And that vector of 32 numbers, that like describes what the key point looks like. But it's better than using just the RGB pixel values, because this is going to be more invariant to things like lighting changes, to things like subtle changes in view. That's why it's called a descriptor. So it's the idea of taking, some pixel values, doing some math. In this case, the math is this binning histogram operation, and computing a vector that should kind of describe those pixels in a more robust way that will not vary from scene to scene. So that's the idea. So what those 32 numbers are then, those are the 32 values that go in to make the descriptor. That's the idea. So that's why we get back this vector. And what I've actually done here, it's kind of boring, but I just wanted to show you. Here I've plotted just as a vector, just as a plot, I've plotted the values for two. I just picked the first key point we detected and the second key point. And I've plotted the values of that descriptor, and they just look like noise. They kind of should. I'll show you a little visualization in a second that's a little more tangible maybe, but this vector, these 32 numbers, should describe what those points kind of look like. And notice that these two vectors are kind of different. They don't agree very well. Like this one goes up, that one goes down, So because they don't agree very well, I'm going to assume that those key points must not look very similar. That's the idea. So we'll kind of tie all this together in a second. So bear with me here. That's the idea there so far, though. So now what we're going to do is we're going to try to match key points between images. That's the whole point here, because let me go back here for a second. We've got our first image, we've got our second image, and our job is to match key points. I want to know that, hey, this point over here in the corner matches this point. That's what I'm trying to do. That's the math problem I'm trying to solve. So, right, so we've got this big list of descriptors from here, this big list of descriptors from here. These are each from our two different images. So we need some function to throw all these descriptors into that can hopefully match them together. And if you think about it, if each of these gives us around 1,500 points, then to do the comparison between all the different pairs, you have to compare 1,500 squared, basically. You have to do a bunch of comparisons. That can be slow, and there's some optimized ways of doing it. We are going to be okay with it being slow right now. We're going to use something called the brute force matcher, BF matcher, in OpenCV. We're going to use, so whenever you're trying to match key points, you need some metric, some measurement that tells you how different two key points are. So here we're telling OpenCV, please use what's called the Hamming distance, to find the difference between these 2 points. And points that have very short Hamming distances will be considered similar. And actually, yeah, I'll just throw this in here for fun. I just got a really cool book in the mail. I have a book problem. I own like way too many books. My wife always gives me crap. But I just got a book by Richard Hamming that just got reprinted. It's called Learning to Learn. I'm going to check this out over the holidays. But Richard Hamming, the person who this metric is named after, really interesting scientist. I think he was an electrical engineer, but developed a bunch of interesting work in algorithms. And yeah, this book called The Art of Doing Science and Engineering. It's kind of like a more of a philosophical book, I think, about engineering work. But anyway, this is one of my reads for the holiday. It still has the shrink ramp on it, so I'm excited. Anyway, I just thought I'd throw that in because I happen to have the book on my desk of the person whose distance we're using. So there we go. We're going to use this Hamming distance to figure out how similar 2 points are. That's the idea. And we're gonna let OpenCV kind of do the work for us. We're gonna let it find the matches. And these matches can be noisy. So we're gonna do one more thing called Lowe's ratio test. And all this does is we go through our matches basically, and we're only gonna accept pairs that don't have like, so let's say you have 3 points, right? Or let me go back to this picture. So here's our 2 pictures. I kind of wish they were side by side, but that's okay. Imagine that you're looking for the match to like this point right here, right? This exact point. And let's say that you search through all 1,500 points over here, and you end up with 2 that have very small Hamming distances that look very similar, right? They have very small distances between them. If you find 2 matches, that's kind of not a good sign, right? It's bad. You'd like to have one really good match and the rest be kind of crappy matches. So that idea is expressed in what's called Lowe's ratio test. It's really simple. It's named for David Lowe, the same guy who invented SIFT. If you filter through these points and you throw away any time that the second best match is 75% as good as the first best match, you throw those away basically. So anytime there are 2 matches that are really close, if you throw that away, then you get better performance overall. So that's the idea. So we're going to do this ratio test. After we do that, we're only going to have 90 matches. And we end up with this matches cleaned vector. And I just wanted to show you this. Here are 2 matches. Here are the vectors for 2 matches. And notice how nicely they align, right? So the key point descriptors for these 2 matches look very similar. To make that a little more tangible for you, I'd like to show you the patches, the little image patches that these came from. So have a look with me here. So these are the 2 patches that made those 2 descriptors. So this is really zoomed in and it's hard to tell what's happening, but that's kind of the world you live in if you're a key point detector. And look carefully with me, right? So these might look a little different, but see this structure here? See this kind of like staple kind of shape? This kind of looks like a backwards C, like the letter C. The same shape is like right here. So see this? Even though the darkness has changed, the overall pattern is very similar. And what orb does is it computes, so notice this is a pretty big neighborhood, right? And if you just did the pixel difference, you might end up with, an answer that doesn't make a lot of sense. But here, these are considered very similar patches because they have a similar pattern. So when I say that a key point descriptor is invariant to things like rotation, then that's what I mean here. See how this little pattern has been kind of rotated over here, a little bit rotated? The key point descriptors, they don't really care, right? So they're still very similar, even though the image has been rotated. So that's kind of an example of how these things are supposed to work. So that's the idea. We're going to do, and there's a few steps I'm kind of glossing over. They're not too exciting. You can look back at the code if you need to. But here's the matches. Here are the matches. And there's some problems, right? So like this pink line, this point is not the same as that point. That's kind of a bummer. But this one looks right. So this point right here appears to have been matched correctly. And if you think about the texture of that brick, that's pretty impressive. And let's look at a few others. I think we'll visualize it a different way in a second. But like this one I think is a little off. This one looks pretty good. Look at this. So right here, that point, appears to have been matched really nicely to that point. So that's impressive. Like that's why these papers are so popular, because doing that is not that easy. So here you go. Here is the optical flow picture from, this is two different views of the same brick and ball and cylinder. And you see some noise, but overall you can really see the motion nicely, right? So it really has learned this pretty well. I shouldn't say learned, there's no learning involved. It really has matched those points pretty well, is what I should say. I'm so used to talking about machine learning. Okay, so here's my animation to show you. So recall that when we used optical flow, we really struggled with a step size of 10. And there's still noise in that bottom right-hand corner, right? There's still some issues, but it's much better. It's much better. Let me just go back to the previous one just to show you. Here is optical flow, where we just search the neighborhood, and look how noisy this is, right? See all those crazy detections, right? And now if we scroll back way down here to the orb-based matching, which is slower, by the way, it's more computational work, but look how much better this is, right? So much nicer detection. If you need to do better than that, let's say you're solving some problem and that's not good enough, right? If you need to do better, the next thing you want to look at is what's called RANSAC. So RANSAC stands for Random Sample Consensus. It's kind of one of those half acronyms, half words. But I have a lecture for it on you. I don't think we're going to have time for it, but it's here. So if you find yourself in a situation where this is not good enough and you want to do better, then you can use a technique called RANSAC to estimate the motion between frames and then throw out outliers based on a model of transformation, basically. So there's some really cool additional math you can do, but we won't quite cover it in this lecture. Okay, so that's orb. That's the orb feature detector. That's matching it and solving a problem. And as far as talking about key points, there's one last thing I want to address, and that's the idea of can we learn this, right? So our interest points in detector is learnable. And I just want to share one paper with you, because everything I've shown you so far it's analytical. So engineers sat down and designed these pipelines, and they work really well in some cases, and in some cases they suck. It just depends on the problem. There's a really cool company called Magic Leap. Somehow they've raised like $2 billion in funding. Last I heard from them, they were having some problems, I think, but they make this. Has anyone used a Magic Leap AR headset? I've heard it's just like incredible, like bananas. Has anyone used one or heard of these things, Magic Leap? All right, no one's used one, or you guys are asleep. I'm not sure. I got to ask a question soon. But Magic Leap makes these AR headsets, and they do a bunch of computer vision research. And yeah, apparently they're just like bananas, like really good AR. Although it's not okay. Yeah. So I've heard they're just crazy. So they raised a bunch of money. They published some research. So some of the research that the engineers at Magic Leap published is a paper called Superpoint. And Superpoint uses a deep learning based approach to learn a key point detector and I believe tracker, or maybe it's just the detector and descriptor. Yeah, maybe it's not the tracker. I'm not, or maybe it is. You have to look at the paper. But there is one thing I'd like to point out about the paper that I really thought was super cool. So let's assume for a second that you worked at Magic Leap. You'd been hired when this company raised $2 billion to work on some cool computer vision problems. And you were tasked with the idea of using deep learning to try to learn a better feature detector, or I should say a better key point detector, right? You want a deep learning model to learn to find good key points to track between frames, right? Okay, so let me ask you this. How do you get your training data, right? Any ideas? How could you make a training data set if you were going to try to train a model to find good key points to track in an image? Any ideas? There's one terrible idea. I shouldn't say terrible, but the painful way to do this. Yeah, that's a cool idea, Abhijit. Put stickers of different colors on the brick. Very cool idea. So there's a bunch of manual ways you could do this, right? You could put stickers on bricks. You could kind of label a data set where you kind of click on the corners of a brick and say, hey, please learn to find these corners, That's a lot of work. What the Magic Leap team did that I thought was really cool is they used a a rendering engine, maybe like Unreal Engine or something, to render images of objects like photorealistically-ish. But if you render an image of a fake object, right, using like a video game library or something, you already know where the corners are, right? So you can use those as your labels. So they can say, let me render an image of a brick or something, and I know where the corners are because I built this from a 3D model. So I kind of get labels for free, right? There's a number of like driving simulators, for example, that use Grand Theft Auto as the to make data, and that works surprisingly well. So what they do is they make a synthetic data set using like Unreal Engine. I'm not sure the technology exactly, but they know where the corners are or the points of interest because they have a real 3D model of the part that they use to make the rendering. They train the initial model with that, and then they transfer to real data. And by starting with synthetic data like that, they do way better. It's really, really interesting. So it's a great paper, and it presents a really cool way to bootstrap your data set to create more data than you'd ever want to label, basically. So really interesting paper. If you're curious, I'd encourage you to check it out. They have an open source implementation for inference, which I have run on our image here. And here's a nice figure from the paper. Yeah, look at this. Like, so we looked at the Harris and the She, and so the fast feature detector, that's part of Orb, I believe. So look at these key points, right? So hopefully you can see this okay. I can't quite zoom in on it. But here, if you can see this, so the magic point algorithm there is, look, it finds exactly the corners of this brick, basically, or this rectangular prism. And look at fast, it's just like everywhere. Harris is everywhere, She is everywhere. So like it does a way better job at finding like the important points of an image, is the idea. So here is a cool animation that this is a movie of the brick ball cylinder, and it's being tracked by Superpoint. So look at how good these tracks are. I hope you can see that in the stream. So I'm drawing a little line, you know, or the rendering part of that library is drawing a little line behind each point. And the tracking is just crazy. It's really, really good. There's a bunch of noise. There's ways to filter that noise. That ransack method I shared can do it. But this blew me away, and how well it's detecting points on the cylinder, for example. You could get this performance, I'm sure, with Sift or Orb if you really spent some time tuning and working on it. But out of the box, this Superpoint deep learning based key point tracker, just like, wow, like it really, really impressed me. At the beginning of this animation, I've just let go of that ball and it kind of wiggles, and watch how good it tracks. Watch this. So whenever this video restarts, right there, see that wiggle? The tracking is just like, it blows my mind. So really, really impressive. And it's interesting because if you're an AR company, right, if you're trying to build AR goggles like they are, if you want to simulate something being fixed in the real world, you have to really, really robustly estimate the motion of the goggles relative to the world to keep the renderings fixed to the world. So being able to do this, right? Being able to do this is so important. So they've clearly invested a bunch of effort. And on top of that, it has to be an efficient and fast algorithm because it has to run, you know, in some goggles, right? I think I believe the Magic Leap system includes a little compute module. It's like a small NVIDIA Jetson computer or something. But yeah, what a crazy computer vision problem, right? I really want to try some of these goggles. I haven't had a chance to, but I talked to one person who used them, and they just said it was like by far the best AR thing they'd ever seen. Like it was just dramatically better than what they'd used before. So anyway, so that is really key point detection. If there are any questions about key point detection, please throw them in the chat window. You'll have a little bit of this on your quiz, nothing too crazy. I won't ask you any math questions about key point detection. Really, I might just ask you to tell me a little bit about SIFT or a little bit about Orb or a little bit about Lucas Canate optical flow. Really, we cover about 5 or 6 techniques in this lecture, and I would like you to know just a little bit about each, maybe the strengths and weaknesses. So, so that's that lecture. So that gets us through interest point detection and description. So if I go back to the schedule here, so now we get to kind of our last little, you know, set of lectures here. And there's one more kind of really cool big area that we got to cover in 3D computer vision. We talked about the pinhole camera model. That was our first lecture. We talked about how to kind of do some basic 3D reconstructions. We then talked about how to find good points to track and to use to make 3D reconstructions. And now we need to really get into models of transformation. Um, and this math, again, it's really important to it's really important to any kind of 3D computer vision pipeline. And actually, yeah, okay, yeah. So the models of transformation, though, I misspoke a little bit. Before we get into that, we first need to talk about camera calibration. Yep, okay, cool. And why is camera calibration important? So for a number of reasons. If you find yourself doing anything in robotics, anything where you have to have an estimate of kind of any kind of measurements about the real world, you're probably going to need to calibrate your camera. And that's what we're going to cover here, camera calibration and image distortion. So it's a really cool little piece of math. It's not too tough. But it's really interesting. I have a friend who's a founder of a startup that does some computer vision stuff, and he is not a computer science major. And he has, like, he's the CEO, and he has a couple engineers who work for him. But he does a lot of technical work, and he had to solve a calibration problem, and he kind of invented this himself, and he spent like 6 months on it or something. And I remember talking to him, and I was like, man, you got to just go read this lecture. Like, you did everything right. That's awesome. But you're working so hard. This is really good stuff to know for a number of different applications, and any time that you need to use computer vision to say anything about real world size or space, knowing some basic camera calibration stuff is really, really valuable. So let's get into it. We've got about 30 minutes left, so that's great. Okay, hopefully everyone's hanging in there. Everyone's alive. All right. Okay. So let's get into it. So we left off, I'm going to kind of pick up where we left off in our pinhole camera model. We left off with this big, kind of gross looking equation. I don't know, hopefully it doesn't look too scary. Let's walk through it together. So I kind of wish I hadn't put the names on here because I was going to ask you what the names are, but we'll walk through them briefly. Excuse me. So remember, we have X and Y. Those are the coordinates of our points in image space. We have U, V, and W. Those are the coordinates of our objects or whatever we're trying to keep track of in world space. We have this intrinsic matrix. So this really captures the way the camera behaves. We spent a lecture talking about this. We've got the what are called the lateral or the horizontal and vertical offset parameters, and the horizontal and vertical focal length parameters, Vx and Vy. And then we have this thing, right? And this captures this idea of extrinsics. And we're going to get more into extrinsics into our last notebook, not this notebook, but the next one. I know we went over these kind of fast, and we'll spend a little bit more time on extrinsics, which is how we move our whole coordinate system around to kind of put the camera where it needs to be in the world to solve whatever problem we're solving. Okay. So what I want to get into actually is the idea that the model of the pinhole camera that I gave you, it's actually wrong. So, and every model is wrong. Some are useful, like George Bach said, but there's a specific problem with cameras that we haven't addressed. So here is a picture of a printed out checkerboard or chessboard, whatever your fancy is, that I have taken a picture of. And it's kind of subtle on this camera. I kind of wish I'd used a different camera, but you'll see it if you look carefully. Do you see any problems? Is anything weird about this picture? Anything, especially if we're thinking about measurement, right? If you look carefully, do you see anything funny about this picture? Tell me more about the edges. Yeah, so Ashish says edges. What about the edges? So yeah, that's a great first thing to say. What about the edges is kind of weird? They're not straight. Yeah, how would you describe, so look at the edge of this piece of paper, right? It starts here, moves like this, right? How would you describe this edge? What word would you use to describe this edge besides not straight? Yeah, it's kind of curved. I would say it's bowed, like it's bowed outward, curved outward. Yeah, okay, so right. And same thing here, right? See how this is kind of curved outward? And it's harder to see, but these are probably a little curved outwards too. So why? Well, why do the edges of our piece of paper, so I could have taken the time to make a crazy piece of paper that's actually slightly curved on the edge, but I didn't. I promise this paper it's square. It's not curved on the edges. Why does the edge of the paper appear curved in our image? What's going on? Any ideas? Yeah, so Hernan says the lens. What is the lens doing? What is the lens doing that makes the edge of our image appear curved? So Ashish says focus on the center. Sure. Tell me about the light though. So cameras, they just capture light, right? When a ray of light, like the ray of light that's coming off my head into this camera, right? Like right here, when it goes through the lens, what happens to the ray of light? Yeah, it diffracts, it bends. Yeah, thank you. Yes. So let's get into that. So the reason this is important is when I showed you this pinhole camera model, right? Um, we assumed, remember we did all that right triangle stuff, right? Right triangles don't have curved edges, right? We assumed that the lines of light were actually straight, right? But I've just shown you that, hey, they're actually not straight, right? They're curved. So that's a problem, right? So the pinhole camera model, it's wrong, right? It's a good model, but it's not 100% correct, just like any model. So what are we going to do about that? In some applications, it doesn't matter. You can just ignore it. It's fine. Who cares? For other applications, robotics, autonomous driving, mapping, things where you really need a good measure of the world, this is a problem, and you got to fix it. So how do we fix it, right? So the next 10 minutes, we'll describe the math that we use to fix it. And it's not too bad. It might sound scary. It's really not. It's not bad at all. Okay. So what we're going to do is we're going to use a model of lens distortion, a model of lens distortion. And this is the model written in math. It's going to be built into OpenCV again, which is really nice. So I'll just walk you through this model really briefly. So this is a model that transforms a pixel coordinate x into a new coordinate x prime. So perhaps that our initial pixel coordinate, maybe this was the 10th row of the image, it might get pushed to the 11th row. It's going to push pixels around. It's a mapping between images, basically. So this is the new coordinate, this is the old coordinate. And what this equation is saying, it's saying, okay, to find the new coordinate, x prime, please take the current coordinate and then add these terms to it. So there's a first term that has x again times k1 times r squared plus k2 times r to the fourth plus k3 times r to the sixth. R is the distance between the center of the image and the point that we're interested in. So it's like the radius. K is just a constant, which we'll get into in a minute. And then finally, there's this other term, and we'll get into kind of what this does in just in one moment. So that's one term. It has the radius and these constants. And there's a second term that has, it also has the XY positions. And it has these other constants, P, and it has the radius again. So it depends on the radius. Now, as you'll see in a minute, these two sections can be lumped together into what are called a radial distortion and a tangential distortion. And I'll show you in an animation what this does. But what I'd like you to see, if you kind of zoom out and don't let this equation scare you, what's really happening is, so remember, x and y, those are the initial pixel coordinates. And to compensate for the bending of the light through the lens, we're going to push our pixels around, right? So where does the pixel xy end up? It ends up at x prime, y prime. And what controls where it ends up is this equation. And the equation has 5 parameters. It has 5 parameters. There's other models of camera distortion that have 8 parameters, more parameters. We're going to use the 5 parameter model. And the 5 parameters are this K1, this K2, this K3, this P1, and this P2. Those are the 5 parameters that describe how the lens distorts light. And everything else is just kind of plugging in numbers. So the radius, you can, if you know x and y, which you do, it's your initial point. To compute the radius, you just plug in, it's x squared plus y squared, and take the square root, basically. So everything else you just plug in. So that's the idea. I hope that makes sense. It's a simple equation that computes where to shift your pixels to compensate for the distortion of your lens. To make this a little more intuitive, I hope, I've made an animation, which I'll show you in a minute. And what the animation does is it basically plays with or perturbs these 5 parameters. So I take that same checkerboard image or chessboard image, and I process it using these equations, which would be like, these are like undistortion, they're called undistortion equations because they remove the lens distortion. And ultimately, we're going to have to find the right values of K1, K2, K3, P1, and P2. We're going to find those values. We'll cover in a minute how we find those values, but for now, I would like to show you the effect that those values have on the distortion model, right? So if I have a big K1 value, how does that change how this model processes an image to undistort it, basically? So that's the idea. So we're about to see an animation where I'll show you the chessboard. I will slowly change each of those 5 variables, and we'll see how our image is warped. That's the idea. So let me scroll down and we'll look at that model together. So here we go. I'm going to wait till the animation restarts to start describing it. So we'll start with K0. So if I take K0, I started from a very big K0 and I scaled it down, and we were kind of seeing how the image changed. And I might wait for it to get back again. You can see I'm kind of going through these 5 things. So here's K0. See how the whole image kind of warps out like this, right? This is called a pincushion distortion. So the whole image kind of warps, right? And what that can do is that kind of distortion, that can compensate for the curvature that we saw in our image. So if you imagine if you just if you unbend it in the right way, it'll be flat again, right? That's the whole idea, right? Can you make things look flat again? And remove the camera distortion. So K1, K2, and K3, those are just different versions of kind of that pincushion flattening, unflattening that we're doing to the image. P1 and P2 are a little more dramatic. They're kind of like whole big twists of the image, right? It's called tangential distortion. But these transformations, they're meant to model exactly, well, not exactly, but they're meant to model roughly what happens to light when it goes into a camera lens. And by applying basically the reverse transformation to what happens to the light, we can basically pretend like the lens isn't there and it's not bending the light. That's the idea. I hope that makes sense. So that's the idea of camera calibration. And let's get into, yeah, I think that's all I'm going to say about the equations. What I want to show you now is how to find those variables. And there's something I didn't quite mention, right? So, you know, well, let me back up actually. So you have this model, right? And we want to find K1, K2, K3, P1, P2 for a given camera. And I kind of glossed over it, but really for a camera, we also want to estimate these parameters. We would love to know the deltas and the phis, because those are going to help us solve all different versions of this equation. And what's really remarkable, it's so cool. There's one algorithm, it's called Zhang's algorithm. It's implemented in OpenCV. And what it does is it allows you to find all of the camera calibration parameters and the intrinsic matrix without measuring anything, which I know seems crazy. It is relative to a scale factor, but it's really, really cool. I've tried to read this paper once, but I haven't gotten all the way, I haven't had time, but I'm always curious about how it works. It seems kind of like witchcraft. Like, I'm really impressed that Zhang's algorithm works so well. And yeah, there's a link to the paper if you want to read it. Let me know if you figure it out. I think it's really cool. It's one of those things I've been wanting to read for years, but haven't gotten to. But let me show you how it works. So there's this algorithm called Zhang's algorithm. It's in OpenCV, and we're going to use it to calibrate our camera. What does calibrate mean? It means find these 5 distortion parameters and find our intrinsic matrix. That's what we're going to do. So here's the camera we're going to calibrate. This is the camera I used for a long time on YouTube and stuff. I just upgraded to a Canon EOS R P, which is really nice. This is a nice camera too, but cameras are getting so much better so quickly. But anyway, this is the camera that we'll use to solve this problem. And just a little information about it. It has a focal length of 14 millimeters. This is a very short lens I'm using. It's a very wide aperture lens. Sorry, wide angle lens, excuse me. The images we're going to take are going to be at a resolution of 2336 by 1752. This will be relevant later. Hang on to that piece of information. And the sensor in here is 17.3 millimeters wide. So like something like this, a centimeter, 0.7. So this is the camera we're going to be calibrating. And this is where it just gets, this is just so cool to me. I think this is just awesome. So all the data that we need to actually calibrate our camera, all we have to do is go take pictures of a flat chessboard grid or checkerboard. That's all we have to do. And using these pictures, Zhang's algorithm is going to compute the calibration for us. It's really, really cool. Like, the fact that this works just blows my mind. So here are a bunch of pictures. Here's 25 pictures or 24 pictures of the same thing at different angles. And we're going to use this to calibrate our camera. So let's walk through the pipeline here. So I'm going to grab one of those images and I'm going to kind of show you how the pipeline works. So here's our image. It's resolution 1752 by 2336. Here it is. The first thing we do is I'm going to throw it into grayscale. I'm going to convert it to grayscale. And I'm going to use a method appropriately called find chessboard corners. I guess OpenCV, the authors have decided that it's a chessboard, not a checkerboard. Notice my chessboard is not 8 by 8. I believe I'm a little hazy on this detail, but I think you do better if you use a non-square chessboard. So here it's 6 by 9 basically. You have to tell OpenCV what your dimension is, and that's the number of interior points. So if you go this way, there's 1, 2, 3, 4, 5, 6 interior points between squares. So we use this method called find chessboard corners. It's really cool. It's such a specific method, but it works really well. So here it is. It has found the chessboard corners. Here they are. I'm plotting them on the image. And now we're going to do that to all of our, to all of our images. And I think we're going to plot them all here, I think. What else am I doing here, actually? Am I optimizing? No, I'm not. I'm not optimizing anything yet. I'm just finding the corners. I'm storing them all in a big list. And I'm also doing one more little thing, this corner sub pix. Any guess what this does? So what do you guys think? So I found the chessboard corners. This is something we haven't talked about a lot in this class, but it's popular traditional computer vision kind of thing. Any idea? What is this corner sub pix thing doing? Any ideas? What am I doing here with OpenCV? So, okay, so yeah, so splitting the corners into pixels. So good guess, very, very good guess. It's actually not quite as cool. So this subpixel refers to this idea of subpixel accuracy. What this is doing is it's just taking those points and the find chessboard corners. It can find the location of a point down to 1 pixel. Basically, it'll be off by a max of 1 pixel in theory. And the subpix method, that actually solves a little equation that actually fine-tunes those points so they can be more than 1 pixel or less than 1 pixel in precision, basically. So it might figure out that a corner, maybe the find chessboard corners thing thought it was at pixel location 11, 12. It might get refined here to be like 11.3 and 12.2 or something. So it just refines the location. So I just bring it up because this idea of subpixel accuracy is something you might hear from time to time. And that's the idea here, subpixel accuracy. Okay. So here is my visualization of all my chessboards. If you look, it's done a really nice job of finding all the points in all 24 images. And now we're going to run this algorithm. I'm not going to run it live because it's a little bit slow. But all you have to do is pass in the points that you found, basically a list of points. And this is just the coolest thing ever. So all the stuff that this returns. So let's talk through it really fast. So it returns 4 things. So 4 things to us get returned. And it's the fact that we can get all this back out is so cool. Let's talk through them. So let's talk through the 4 things that get returned. First of all, intrinsic P. Any guess what that is? I've given it a variable name here. Hopefully it's a helpful variable name. What is intrinsic P? There's kind of a hint on the screen. Yeah, it's the intrinsic matrix. Yep. Yes, Aparajitha. Yes, it's the intrinsic matrix. Yep. So that's what we were looking for. We'll go into whether or not it's a good one or we like it in a second. But this is the intrinsic matrix. The distance, we'll come back. Actually, sorry, this is for distortion. So DIST, these are the distortion coefficients. Remember those 5 numbers we were trying to find? That's exactly what that is. So the one thing I do want to ask about though, just briefly, is RVEX and TVEX. This is just the coolest thing to me. So it also returns an estimation. So R is for rotation, T is for a translation. This method not only gives you the calibration, it tells you where the camera is located relative to each chessboard. Right, so this is going to be a list of 24 vectors that describe the rotation of the camera, and this is a list of 24 vectors that describe the position of the camera relative to the chessboard. So you're getting back not only the calibration, but the location of the camera in those instances. And this is not just to be nice. You actually have to compute these to solve the problem. But it's cool that you get all that back out. That is really neat to me. Let me bring up something. So A minute ago, I told you the resolution of our camera. I said, hey, our camera is, what did we say? So the camera resolution is 2336 by 1752. Okay, so that's our camera resolution, right? Okay, and the reason I bring all this up, I just copied it because we'll need it in a second. Here's our intrinsic matrix, right? This is what came out. And when you get one of these out, it'd be nice if there was a way. How did I copy this? Like that? Yeah, like that. Cool. Okay. So we want to know if this matrix makes any sense, right? Does this seem like a reasonable matrix? So let's look at it together. So here it is. And remember, just the one last thing I want to point out. So remember these two parameters, delta x, delta y, right? Does anyone remember what was the connection between delta x and delta y and the resolution of our camera? How were these parameters connected to our camera resolution? Mm-hmm. Thank you. Yep, so that's stuck from last week. That's good. All right, so it's half, right? So if our camera is a horizontal resolution of 2,000 pixels, then the delta x value is 1,000. It's half, right? Okay, cool. Let me ask you this then. So if our calibration worked, and if this is the resolution of our camera, what would we expect delta x and delta y to be? What would be reasonable values? What would we expect roughly? Any ideas? Because remember, we just took a bunch of pictures with this camera. We took 24 pictures of chessboards. We ran this thing called Zhang's algorithm. It's supposed to tell you, it's supposed to compute, this value, this value, this value, this value, plus the 5 distortion values, which we'll get into in a second. But it's supposed to compute these for us, right? So if this really is the right resolution, right? If this is the resolution, right? What should the value of delta x and delta y be close to? What do you guys think? If this is the resolution, 2336 by 1752, what would your delta x be? What would you expect it to be? Yeah, it's half of the size. Thank you, Monica. Yep, so 1168, perfect. I think that, yeah, sounds right. And then 876, right? Cool. Okay, so let's go see. Let's see if that actually worked. So we ran Zhang's algorithm, right? And the output was this. Here it is. Let's have a look. So for delta x, we are getting 1161 times 10 to the third. So that's equivalent to, oops, come on now. There we go, cool. That's equivalent to 1161, basically. So, so Monica said 1168, and Zhang's algorithm said 1161. So that's pretty good, right? It's pretty close. And remember that the actual camera could be a little different because the image sensor might not be perfectly aligned. So this might actually be a better answer. But yeah, we want to make sure it's kind of in the neighborhood, because if it's not, there might be a problem, right? There could be a problem in our pipeline. And then Monica, for the delta y, she said 876, and Zhang's algorithm said 858 times 10 to the second. So yeah, so 858. So yeah, that is, how did we do on that one? Yeah, actually, yeah, not bad. 20 pixels off, not terrible. So yeah, not bad at all. Where you'd be concerned is if this had been like 8,000 or something, right? If it was like an order of magnitude off, that'd be a little bit concerning. So, so that's great. That's awesome. These are a little bit less interpretable, but in a minute, I think we are going to try to interpret them. But we got values of around 2,000 for the focal length parameters. Just one thing I want to ask the class. We covered this very briefly, well, in some depth on last Tuesday. Notice that these numbers are pretty similar. So this is like 2003. This is like 2002.7 or something. How do you feel about these numbers being so close? Is that a good thing? Is that a bad thing? Does anyone remember, what does that mean, right? What does it mean that these numbers are close? Yeah, so Aparajita says they need to be the same. They're going to be the same under one assumption. Does anyone recall what assumption that was? There's one assumption that needs to be true about our camera. It has to do with the pixel spacing. What was the assumption under which these should be the same? A good guess. So Hernan says 1 pixel equals 1 millimeter. Not quite. Remember, this is like an X value. Good guess, Hernan. This is an X value. This is a Y value, right? And they'll be different. These will be different if, and these are the focal length parameters. They will be different if the pixel spacing on the sensor, if it's different in the X direction than it is in the Y direction. It's rare that those would be different, but they could be depending on your camera. But for this camera, I know, and for most DSLRs and stuff, the pixel spacing it's pretty much the same this way as it is this way. So they should be the same. So that's a good sign. Okay, so that's our calibration matrix, or our intrinsic parameters, excuse me. And these are the distortion coefficients. So for these, it's going to be hard to know, like, is that a good value? You know, who knows, right? Let's actually visualize what happens when we use those values. So I think, yeah, this is just me in the notes talking through the ideas we just discussed. And now let's look at image undistortion. So what's really cool is that, you know, I said all of a sudden I was like, hey, you know, the model I taught you last Tuesday, this pinhole camera model, I said, hey, it's wrong, right? It's not actually correct. And what's really cool is if we were able to compute those 5 parameters that describe undistortion or describe the distortion of the lens, we can do a process called image undistortion that will make this model true again, right? If we apply this process to our images, then the pinhole model will work again. So what is that process? It's called undistortion. Let me walk you through it. It's really, really straightforward. All we have to do is we take our image, we run it through a method called CV2 undistort. We pass in the intrinsic parameters and the distortion coefficients, and it basically does its very best using the parameters. I shouldn't say does, it just solves it plugs into a very simple equation. It's actually the exact equation, well, I can show you. It uses this equation. So it plugs in the image pixel points and it plugs in the parameters into this equation, or these equations, and it computes your new image. And your new image, if we've done our job correctly, should not have curved edges. It should not have curved edges. So let's see. So here's the original. See the curved image here, right? Curved edge. And here is the new one, right? So here's old on the left and new on the right. And it's fairly subtle, but you can really see a difference. And especially for me, like if I just kind of blur my eyes a little bit, in hindsight, I wish I had chosen a more dramatic camera lens. It'd be more obvious. But I hope you can see that. Hopefully to you, to me, if I just kind of look and blur my eyes a little bit or just kind of look roughly, the one on the right looks much more flat and the one on the left looks like it has this kind of distortion to it. If you look at the top edge, it is straighter here, but it's not like perfect, but it's significantly better. So this is the idea of undistortion. So we're getting rid of those curvatures that come from the edge of the lens. And the wider the angle of the lens, the more curved the edges will be, and the more dramatic this effect will be. Okay, and the thing I really want to emphasize is that if you do undistortion, if you do this undistortion process before you do your rest of your math, then the pinhole camera model is valid again. So basically it saves our model. so that's the idea of calibration. I think that's all I'll say on calibration for now. We've got about 5 minutes left. I might be able to just kick off the next lecture just really briefly. But this is the idea. That's the idea of camera calibration, undistortion. I hope that all makes sense. Again, these are the techniques that, you know, you may, if you end up doing something in machine learning or deep learning, you may not use these too often, but when you need them, these are great techniques to have, especially if you're doing anything with robotics. I hope that this is a lecture that later in your career you may pull back up just to remind yourself how to do something. I hope it's a good starting point then. That's kind of the idea. I want to make sure we cover these topics in some amount of depth because they do come up. Okay, yeah. So Monica asked, do I use deep learning in my work? Yeah, definitely. So yeah, in my current job, I do almost no camera calibration. But in my old job, I did a bunch. I did a bunch of some of the stuff I'm showing you here. I figured out at my last job because I was working in autonomous driving. So it's like robotics. So you got to estimate distances. In my current job, I do a ton of deep learning. The most relevant module to my current job is definitely the deep learning module. But this stuff is important too, depending on what you're working in. So yeah, And again, it's a little bit less common than deep learning today, but still really important. And you'll be surprised where you bump into it. People just don't know about these techniques, and they've been around for a while, but they're really powerful. Okay, I'll just set up our last lecture, and if you have any more questions, please throw them in the chat window. We've just got about 5 minutes left. I want to just set up this will be our very last lecture that I deliver. It'll be on Thursday, in 2 days. On next Tuesday, we have Thomas from Instagram who's gonna give a guest lecture, which I think will be really cool. But Thursday is my last lecture. Pretty crazy. I hope the next time I lecture, which will probably be 2021 fall, I hope it's in person. This has been fun. I've liked hanging out on Zoom with you guys, but it'd be more fun in person. So we'll see. I guess next semester is fully online though, which is pretty crazy, but I'm actually not lecturing next semester. Okay, so transformations. So just to introduce this lecture, I hope is going to tie everything together. Because what we're going to do in this transformation lecture is we're going to like literally map from world coordinates to image coordinates to world coordinates for like points that I've actually measured in the real world. That's kind of the idea. What I've done here is I've set up kind of this little test bed for us. And this is going to get us talking into all kinds of models of transformation for images, basically. You'll see why it's important shortly, but transforming one image into another, whether the first image is a view of something and the second image is a different view of the same thing, or if you're trying to create like a bird's eye view of a road, for example. There's a bunch of examples of where this is useful, but we'll get into it just by looking at some measurements and some math, basically. So what I've done here is I've carefully measured a grid using a millimeter ruler. And I put 4 points on the grid: point A, point B, point C, and point D. And those points are 50 millimeters away from it's 50 millimeters as the X value and 50 millimeters as the Y value. Notice that my coordinate system is a little weird here. I've set up my camera so the center of the camera is pointing right at the center of this axis. And notice that what's a little bit funny, have a careful look at my plot here. What's kind of funny about my axes? What's kind of maybe different than a typical plot? What do you notice? What is a little bit different here? Maybe that -50 kind of throws you off. Yeah, the Y is flipped, right? Yep, thank you. Yep. Totally. So Y is flipped. So why would I do that, right? The reason is if we look at our coordinate system, I'm kind of sticking with our original coordinate system to make life easier. If I go back to the pinhole camera lecture, if we look at our world coordinate system, notice, here we go. So yeah, so positive V is down, right? So if you look at my picture here, I have the V-axis going down, it's just to match that coordinate system. And I have the U-axis going left to right. Because what we're about to do, it's really cool. We are going to confirm and to test that the math actually works to map from a point in world space to a point in image space. And to describe a point in world space, I need 3 values. I need the U, the V, and the W, right? Just to pop back here for a second, right? I need U, V, and W, those three the 3 values that describe where the point is in 3D space. Okay, so this point, for example, A, it has a U value of 50. It's 50 to the right of the center, and it has a V value of -50, right? What value am I missing? What else do I need to measure? What's the one value I'm missing here to describe where that point is? Yeah, W, right? How should I measure W? So I've kind of shown you how I measured these. I just used how do I measure W in a setup like this where I have a camera overhead pointing at a piece of paper? How should I measure W? If you were standing next to me while I was taking the picture, how would you recommend I measure W? It's the height, sure. It's the distance between the paper and the center of the lens, basically the optical center. So I'll show you measuring that now. Get ready. We're going to use a very advanced measurement technique. Here it is. Yep, there we go. So here's my camera setup. Here's my very advanced measuring technique. I'm using again, just a ruler to measure how far it is. And I get a W value of 310 millimeters. So that's the W value. So I want to walk through this whole equation. I want to make this whole equation real for you, right? Because this maybe, I've kind of glossed over it. I want you to feel as comfortable as possible. And I'll ask you a quiz question or two to solve versions of this equation because it is the most important equation in this module. This is like the back propagation of 3D computer vision. It's critical. So to solve this, we need to find some values. Happily, in our last lecture, we found lambda. We found the intrinsic matrix. I grabbed it from here. And we're about to work on those extrinsic. So it's 3:45. I'm going to leave you with this to think about till Thursday. Please go have a little thought, have some thoughts about what this extrinsic matrix should look like. All right, so I've described the setup to you. I've got a camera over a plane, right? And I'm trying to figure out, okay, what is that? So I know the intrinsic matrix, we just solved that with camera calibration. We actually figured out U, V, and W pretty quickly. U and V are just kind of described here. W is the distance, which is 310, right? So what's the deal with this, right? What should all those numbers be, right? Because if I get all those numbers right, then I should be able to plug in, 50, -50, 310, and I should get out exactly where that point is in image space. Like that's the idea. So that's what we're gonna do. So yeah, have a great rest of your week. Keep working on your projects and your programming challenge. You will have a quiz a week from yesterday. Again, just review the lectures, make sure you feel good about the questions that I've been asking. But other than that, have a good week, and I'll see you next time for the my last lecture of the year. Thanks, guys.